Hi everyone, Danny Shapiro from Nvidia. It's great to be here again. And I want to compress 365 days of research into the next 15 minutes. So I think we're going to go really, really fast here. It's a really cool time to be involved in this industry. But it's just a cool time to be involved in technology. There's so many amazing things going on. I mean, Nvidia has been involved in gaming. It's just going through a huge boom. There's an article in the New York Times the other day. The newest game, Fortnite, just came out, and in the first month that there's like 150 million people playing these games. Esports is going crazy. Twitch, which is people watching other people stream games and play games. There was 128 million hours broadcast on Twitch of people just playing Fortnite. So gaming is going nuts. I think we're seeing artificial intelligence just take off across all industries, and again, why we're all here, autonomous vehicles. What I want to do is I'm going to bring all these things together and kind of give you some insights into how all these different technologies, though, are really interrelated and how they're really going to help us develop safer self-driving vehicles. In the Valley, it's also it's on fire in terms of all the auto companies coming out here. This is a CBRE real estate firm that put together this map. And this is now actually 6 months old. This is from November. There's probably been more. But everywhere you go now, there's either an automaker, a tier one, other tech companies that are getting into automaking in some way, shape, or form, the sensor companies. Everybody's here. It's really super exciting place to be. And the reason is basically everything's going to be autonomous. So not just cars, it's trucks, it's buses, it's shuttles, it's bots. It's going to be the Amazon effect. Things that need to get delivered will be delivered to you autonomously. So we're working with over 370 different companies that are working on our Drive platform for autonomous vehicles of some shape, size, form. Somebody said ships, yeah, eventually. I mean, trains, planes, drones, all these kinds of things are all interrelated. The challenge we all know, right, is this is hard to do, right? There's so many different things that the vehicles need to be able to see, sense, understand. So whether it's LiDAR, whether it's these kinds of cameras, there's just such complexity, different types of weather, different kinds of road conditions, things that are occluded, things that humans are doing out there that are crazy and we need to interpret. And so it's not just enough to have these good sensors, but you need to be able to develop the algorithms to take that data and make really great sense of it. So AI, and this is not really up for debate anymore. In the past, it was just kind of pure computer vision. But over the last several years, AI is shown to be far superior in terms of being able to do superhuman levels of perception. And so being able to find things, to be able to understand and predict what they're going to do, to be able to plot paths, AI is really at the core of all this. And so what we see, again, is a whole variety of different neural nets running inside the car. Here's just a sample of a couple of them. But you're detecting things where you want to be able to have redundancy and diversity for extra reliability, for extra security here. So we're detecting objects, but we're also detecting free space. We're running different kinds of neural networks in the car. We're able to sense distances, of course, as we've discussed already. Understand how to operate in different kinds of weather conditions, different kinds of weather and lighting conditions, be able to process all different kinds of sensor data. So we're training neural networks on camera data, we're training them on LiDAR data, we're fusing that data together. And so again, a whole robust suite of neural networks will be running in these cars simultaneously. So what I wanted to show this, I know, Alan, you're very excited about. This is work that's done fairly locally. So we have an R&D facility here in Holmdel. And so this was end of last year. But again, taking some of our research, putting it out on the road with a safety driver. But time lapse, Alex isn't here, but he'd probably be envious of how fast we're driving there. No, so basically, though, being able to detect a lot of different things, be able to do path planning, be able to do weight states, understand intersections, do all kinds of complex turns. So this is the kind of research that we're doing and providing the foundation for our customers and partners to build on. Of course, all this comes down to individual frames, right? Every one of these videos is 30 frames a second. And essentially what we need to do is be able to train these neural nets how to detect what's going on here. This is a very important slide because on that slide are hopefully Princeton class of 2024 and 2028, my daughters. We'll see what happens. I hope so. I hope so. No, but essentially what we're finding is there's a massive amount of data. I don't think anyone has really come to terms with how much data needs to be processed to develop these neural networks. And so what we've been doing is working on a whole perception infrastructure, right? This is a massive supercomputing problem in the car, but it's an even larger scale supercomputing and data problem in the data center. And so we've developed a whole workflow where you're collecting data. You have to ingest massive amounts of data. We're talking petabytes of data coming in. Being able to label those frames. So we actually have over 1,000 people that are working to analyze these data sets, label these data sets, and use them to train the neural nets. So we do that on GPUs in the data center. Essentially, everybody, including Google, is using our GPUs to train their neural nets. So we have libraries of data. We have data coming from vehicles that we're training, and we're iterating. We're constantly then able to test and validate these neural nets. This is what's key. And this is really the next wave of using a data center, using supercomputers to be able to validate that these neural nets do what they're supposed to do. So creating this whole workflow, automating it, being able to then reproduce it, being able to trace it, be able to experiment. Everyone who's working in AI now, it's still at this new discovery level. How do we take this new computing model and apply it in new ways? And it's really an evolutionary process. Data scientists, researchers, and industry together are now kind of reinventing business practices and processes to be better than they were before. So data now is really the new source code. Software essentially writes software, and it's this continuous process of making it better and better. But to be able to create all these different neural nets, to be able to test and validate them, there's no way we can drive enough miles to do so. We've talked about how we drive trillions of miles on the road. Now, if you have a fleet of just 20 test cars, you're only able to cover about 1 million miles in a year, just operating those pretty consistently throughout every day. It's not enough. RAND has the study, I think a lot of us have probably read it. They're talking about billions of miles needed to be able to showcase that these autonomous vehicles will perform better than humans. And so there's no way in our lifetimes that we can drive enough miles to collect enough data to be able to train these systems and validate them. So what we're proposing is using simulation. Now, if you go back to the beginning of Nvidia, this is what we're all about, right? We were the video game company. This is what a video game looked like maybe 10 years ago. And nowadays, with all the work that's going on in Hollywood based on our technology, this is kind of state of the art, where we're doing ray tracing. We're able to actually model the physics of light and create reflections and refractions and be able to do this in real time now for video games as well as in the movies. And so that original video game now looks something like this. Looks pretty good. You're able to model the physics of what's going on, get realistic reflections, refractions, lighting conditions. We've been doing simulation for a while. This is something that related earlier. I added this one slide after insurance talk, but just to show you how simulation is being used in industry from a design perspective, but it also in crash tests. And here we have both a simulated crash test where we've modeled all the physics, all the structural integrity of the vehicle and the materials. And so engineers are actually using this technology now to make cars safer, to be able to make them more cost effectively, and to make them faster in terms of their time to market. And so we can use simulation in many different ways. And so what we want to do now is really move to simulating all these test drives. And so we just brought out something called Drive Constellation, where we're putting all this up in the cloud. So we have servers of GPUs where we're basically generating what the sensors see. So we build a whole environment on one server, and then what we do is the output of the first server goes into our Drive Pegasus, which is our self-driving system that we're actually putting on the rack in the data center. So the system thinks it's actually in the car. It's getting sensor data, but instead of real sensor data coming from the cameras, the radar, the LiDAR on the vehicle, it's getting them from a virtual environment, in VR essentially. And so we're able to then run the software in the cloud, pretending as if we're driving, getting real data, and then actuate the vehicle that's actually being simulated. So I'll show you an example of what I'm talking about. So essentially here, this is the setup of the scene, right? We import an environment. We can create different types of lighting conditions. We can do things that can't be done in the real world. We can move the sun horizontally. But now the key thing here is that we can create hazardous driving conditions. We can create blinding sun at sunrise or sunset. Now, when you're trying to collect data, you only have a few minutes each day where you can go out on the road and actually get that kind of situation captured for your training sets. Here, we can drive 24 hours a day at sunset. We can make it rain. We can make it snow. We can create shadows across the road. So we can create all different types of weather and lighting conditions that you just don't capture when you're doing these test drives. The other thing that we do is now we configure the vehicle. So we can place sensors. We can put 4 cameras on the car. We can put 6 cameras on the car. We can adjust the locations of those sensors. We can put LiDAR. We can put radar. And the cool thing about this is that it gives us the ability also to, again, experiment. What is the optimal configuration for sensors? Right? How many sensors do we need? Where do we need to place them? So we can run a lot of simulations and compare the results of these different tests and be able to see where the deficiencies are, where the redundancies are, and come up with the optimal configuration. So essentially, once we've built the environment, once we've put the sensors on the car, now we can go for a drive. So what we're doing here is, on the left is our drive sim software. And essentially, it's off on the highway here. The output of the server on the left, 1 GPU per sensor, is now feeding those inputs into the Drive Pegasus in the server on the right. So the screen you're seeing is actually the software, our Drive AV software stack, that's doing the basic detections that we've been talking about already today. Then the controls, the output of the Drive Pegasus goes back into the Drive Sim software to actually control the vehicle. So we're able to then start these drives and log miles 24/7. What we can also do in this case is have a person in the loop. So if we want to add another vehicle, a human-driven vehicle, into this simulation, into this VR world, we're able to do that. So now we can test how would our self-driving car behave with a crazy Ferrari driver modeled by the human who's using the game controller to drive that vehicle. And so we can also have a variety of other vehicles in the scene. We can add the number of sensors. So what we're showing here is, again, we're simulating the environment. We have a front-facing camera. We have a rear camera on the top. We have the right and left rear view mirror cameras. And as the different vehicles move through the scene, we're able to detect them and take appropriate action. So again, though, this is running a full drive software stack that we will put in the vehicle. We're able to validate everything in the data center before it even gets out onto the street. There's a lot of different ways then that this can be used. We can also do it at night. And so here you see, again, the creation of all kinds of other scenarios, both ones that we can script. We can also have AI agents. So different cars are going to be controlled by their own AI agents and behave in different ways. Here we have a police car that comes up. And so we can test all different kinds of scenarios, basically build an enormous library of these and continually rerun them against algorithms. In this case now, what we're doing, again, is showing the algorithms that are running. So the output of the simulator gets fed into the drive system to actually run the software stack that goes in the car. And so we're able to do detections 360 degrees around. This is something that we're building, again, for our use, to be able to validate it. And then our customers who are actually putting the cars on the road will be able to test it in the data center before they put it on the car. So the key thing here is there's a whole workflow, a whole process that needs to be defined, from the collection of the data to the training of these neural nets, being able to simulate and validate, and then actually put those algorithms in the car on the road. So the benefit that we've developed now is this whole end-to-end system that's all based on the same architecture. And so what's developed runs both in the data center and in the car, and is going to allow us to achieve those billions of miles to put these vehicles on the road in our lifetimes. Thanks a lot.
We've got one question. Those of you who don't want to hear the question, you can start getting your food. I'm going to leave my presentation till the end of the day, so go ahead. So you don't need to hear me. We're only 50 minutes behind. So some of you want to start getting food, go ahead.
I'll answer questions during lunch. That's fine.
How can you do the certification?
Which certification are you referring to?
SIL 4. SIL 4.
Software in the loop. Are you talking about software in the loop, or?
No, not software. Safety integration level 4, which is the airline certification. So if I want something which has 1/4 every 10 to the 9 hours, how do you certify?
So what we'll be able to show is based on all the different types of scenarios and corner cases and miles. I mean, it'll be statistical math that we'll be able to test and validate against all those scenarios. But in terms of regulation, I think that's part of the workshop tomorrow in terms of what is that suite of tests that a vehicle needs to have. That's not going to be us that will create that. I think we'll be part of that, and we'll be able to use this system to showcase, and we'll be able to run millions of scenarios of pedestrians crossing streets and cyclists, weaving through traffic and things like that. And so the point here is that this is the tool that will be able to be used to achieve whatever guidelines or regulations get put in place.